Hello everyone, welcome to the last problem solving session of the course Introduction to Lasers. We'll start after a few minutes. Let's just wait for others to join. Hello everyone, welcome to the last problem solving session of the course Introduction to Lasers. I am Haskar Dey. So today we'll talk about some interesting topic in the field of ultrafast optics, because after learning about the mode locking we have known that we can actually generate pulses with pulse duration of few femtosecond. So we can have pulses of few femtosecond now. Now this uh, ultra short pulse can have very high peak intensity. So this when a pulse can have a high peak intensity, so it can introduce the non-linear effects in the medium because of this high intensity. The high intensity means that it has a very high electric field. So now from starting with the lasers generate coherent radiation at many wavelengths. So this wavelength range from millimeter wave to soft X-ray region. So now in order to generate, so when these lasers were being developed, there are multiple regions where the lasers were absent. Basically, you do not have the wavelength of that particular region from the laser, so that's why you needed a technique to generate that wavelength from that other particular wavelength. So an entire field evolved associated with the generation of coherent wavelengths by using lasers as the initiating source to produce other useful wavelengths by a nonlinear interactions of the laser beam with various materials. This field involves mostly second and third order nonlinear processes, which are described briefly in this chapter. Such processes have been used successfully in many commercial products. Frequency doubling and tripling of near-infrared solid-state lasers is a particularly significant application of these processes. So first, wave propagation. In an anisotropic system. So the optical properties of most materials are isotropic in nature. That means that a beam of light interacting with the material will be affected in the same way no matter which angle the beam is directed with respect to the material. So this is true for gas, liquid and most solids. However, there are a number of crystalline solids that are anisotropic. The two types of anisotropic crystal are uniaxial and biaxial crystal. So in anisotropic crystal, basically the properties depends on the angle of beam propagation. So now the crystals that has the cubic symmetry are all isotropic. So the isotropic crystal doesn't uh, depend on the angle of beam propagation. Now if the crystal have a trigonal, tetragonal and hexagonal symmetry, they are all uniaxial. And then if the symmetry is orthorhombic, monoclinic, triclinic, these all are biaxial. In an isotropic crystal, the index of refraction of the material is the same in every direction. So the velocity of a beam passing through the material is also same in every direction, but in anisotropic the refractive index is not same. So there exists a orientation of the crystal for which two orthogonal polarization of the beam would see two different indices of refraction in the material and thereby propagate at two different velocities. In a uniaxial crystal, there exists one orientation of the crystal for which the index of refraction and wave velocity are independent of the polarization of the beam. This defines the direction of optic axis of the crystal. For biaxial crystal, there is no orientation for which the index is same for two orthogonal polarization. So now the polarization is changing due to the interaction of material and light. So polarization response of materials to light. So now the polarization, the relationship between the polarization and the electric field is P chi epsilon naught E. So here P is the polarization, E is the electric field. The factor chi was suggested to be a useful parameter when considering the material response to electric field oscillating in the optical frequency range. Now when the electric field is increasing, so basically we are going towards the ultra short pulses. So when the electric field is significantly increased, nonlinear interaction begin to occur within the material. Then this polarization is equal to epsilon naught chi 1 E plus chi 2 E square plus chi 3 E cube plus dot dot dot. So this polarization makes a significant contribution to the nonlinear optical processes. Sorry about that. Nonlinear optical processes, since it results from charges oscillating from charge oscillating within the medium that are produced by the incident oscillating electric field and radiate, thereby adding to that field. For simplicity, we have expressed P and D as scalar quantities. We refer to the chi as susceptibility. Now the chi 1 Now chi's are susceptibilities. Now this chi1 is the linear susceptibility. Chi2, chi3, these are referred as second and third order Nollian optical susceptibility. Second and third order nonlinear optical susceptibilities. So the second order polarization can be defined like this, and the third order can be defined like this. So now these two processes are different from each other. Now if the materials are centrosymmetric, that means that it has inversion symmetry. There is inversion symmetry produce no second order. So in this kind of material there is no second order polarization. So now the magnitude of the nonlinear susceptibility coefficient are such that the second and third order polarization become comparable to the linear polarization term E1 when the applied electric field E is of the order of electric field produced between the electron and proton of hydrogen atom. Thus the second and third order susceptibility are of the order of this. Chi2 is 2 into 10 to the power minus 11 volt. Chi3 is 4 into 10 to the power minus 23 meter per volt. In the following sections, we will briefly describe a number of nonlinear processes. So in the following section, we will describe it. So the second section of this class will go to the second order nonlinear optical process. The first one of this section is second harmonic generation. The electric field is E0 e⁻ I omega t plus E naught star plus I omega t so this is the electric field. Now if there is assume an intense laser beam of angular frequency omega 1 is passing through a crystal having a non-zero second order polarization or a non-zero value of chi2 such that the emerging beam from the crystal will have the angular beams of angular frequencies of omega 1, which was the input beam, and also omega 2, which is 2 omega 1, twice the frequency of the input. So let's assume that this is the electric field that is passing through the crystal, and due to the second order polarization we will have epsilon naught chi2 e squared, so epsilon naught chi2 e star e plus e star plus e square e to the power minus 2i omega t plus e square e to the power plus 2i omega t this can be written as 2 epsilon naught chi2 e star e plus 2 epsilon this is epsilon naught chi2 square e to the minus I to omega t plus epsilon naught chi2 is e star square e to the I to omega t. So the first term is time independent factor that produces no oscillating electromagnetic radiation. It is a DC electric field response referred to as optical rectification. And the second and third terms can be seen to contain frequencies that are exactly twice the frequency of the fundamental wave. So these terms can lead to a significant output from the material to an angular frequency of 2 omega. So these two terms can give you the beam of angular frequency 2 omega. So this phenomenon is known as the second harmonic generation, but of course in order to generate this 2 omega frequency there are certain conditions that needs to be fulfilled, which is known as the phase matching. Now if we want to explain this second harmonic generation with respect to the energy states, then So from photon standpoint, there is that we will consider this energy level diagram. So two photons of the fundamental input frequency omega is absorbed, so that is h bar omega, combining to produce an energy of 2h bar omega, and then there is a single photon is emitted of 2 omega frequency. So basically here two photons are destroyed to generate one single photon of 2 omega frequency. Now we go to the next phenomena, that is known as sum and difference frequency. So in the previous discussion we are talking about that two photon is combined and giving so combination of two photon is giving one photon of a double frequency, but now here the two photon has same frequency omega, but what will happen if we have omega frequency omega 1 and omega 2? Plus e1 e to the power minus I omega 1 t and plus e1 star e to the power I omega 1 t plus e2 e to the power minus I omega 2 t plus e2 star e to the power I omega 2. So now if we use this electric field, then P2 is 0 chi 2 e square so epsilon chi 2 e square, which is epsilon naught chi 2 e1 square e to the minus I 2 omega t plus e1 star plus E2 square theta minus I to omega t plus E2 star whole square theta minus I to omega t plus 2 E1 star plus 2 E2 star plus 2 E1 e to the power minus I omega 1 omega 2 t plus 2 E1 E2 star E1 E2 so 2 E1 E2 star 2 E1 star E2 star e to the power minus I omega 1 plus omega 2 t plus 2 E1 E2 star minus I omega 1 minus omega 2 t plus 2 E1 star E2 E1 minus I omega 1 omega 2 t. So this include the DC term, second harmonic term, and two new terms involving omega 1 plus omega 2 and omega 1 minus omega 2. So if you look at this term, so you can see this is the 2 omega, this is omega 1 plus omega 2, omega 1 plus omega 2, omega 1 minus omega 2, omega 1 minus omega 2. So 2 omega 1, 2 omega 2 are second harmonics generation. This is the sum frequency generation. This is the difference frequency generation. So in this sum frequency generation, a new photon is created by destroying one photon of omega 1 and one photon of omega 2. In the difference frequency, the photon of higher frequency omega 1 is destroyed, while both omega 2 or omega 3 are created. So basically here omega 1 is destroyed and then omega 4 and omega 2 is generated. Now the topic we'll have is optical parametric oscillation. So in case of difference frequency generation, we realize that the frequency omega 2 is amplified while the frequency omega 3 is being generated. So this amplification can be enhanced by placing the optical harmonic crystal within an optical cavity in which the mirrors are specifically made reflective at the frequency of omega 2. Thus, the intensity at the frequency will build up within the cavity as described in the Fabregat's interferometer. So this will increase the intensity of omega 1 and will also generate more intensity at omega 3. Such an amplification process is known as optical parametric oscillation. So here we have three energy levels. Obviously these all are virtual levels. So this is the pump omega 1, this is the signal omega 2, this is idler omega 3. So this is the pump. So there is a photon omega 1 is absorbed and then the two photon is generated from there, that is one is omega 2 and another is omega 3. So the intense input beam at frequency omega 1 is known as the pump frequency. The desired amplified frequency at omega 2 is the signal frequency and the unwanted frequency omega 3 is the idler frequency. This process is used most often in the infrared frequency range where tunable lasers are not as readily available as in the visible portion of the frequency spectrum. Now we will go to the next process, that is the third. It is the third order nonlinear optical process. So here we will consider the P3. So in case of second order nonlinear optical process, those processes are only applicable to the optic material which are non-centrosymmetric, but the third order nonlinear optical process is applicable to centrosymmetric and non-centrosymmetric materials. So it's basically applicable to all the materials. So here the input beam is of angular frequency of omega 1. So it is transmitted through an optical material which could be a liquid, solid or gas. Emerging from that material would be a beam consisting of not only the fundamental frequency omega 1, it will have omega 1, 2 omega 1 and 3 omega. These three frequency will be there. So basically in third harmonic generation we will not have these two frequencies, we will only have this frequency. Now, mm, now let's assume that the input being has the electric field of E1 cos omega 1 t. Now the P3 is chi 3 epsilon 0 E3Q. So now this is the cos q omega 1 t. So if we simplify that with using a trigonometric relation, we'll have 1 by 4 cos 3 omega 1 t plus 3 by 4 cos omega 1. Okay, so the first term, so this term will give us a beam of 3 omega 1. So the first term contains an electromagnetic wave of frequency 3 omega 1. So this is the term associated with the process of third harmonic generation. Now we can again explain this phenomena using the virtual levels. So for this particular phenomena, how many virtual levels do we need? We need 3 virtual levels. Now there are 3 photon is absorbed, or 3 photon, rather I should say 3 photon destroyed, and 1 photon of frequency 3 omega 1 is generated. Now if the input beam has frequency of omega 2, omega 1, omega 2 and omega 3, then with the help of the virtual level we can represent this phenomena. This is the ground level, this is one virtual level, this is another virtual level, and then this is the another virtual level. So this is omega 1, this is omega 2, this is omega 3. Omega 4 equal to omega 1 plus omega 2 plus omega 3. So this is the known as the 4-wave mixing. Now again we can have a different kind of fluoride mixing. So here we one two photon is destroyed. So two photon is destroyed and then two photon is generated. So these are the angular frequency of the two photon that are destroyed. So omega 1 plus omega 2 equal to omega 3 plus omega 4. So these two processes are known as Fourier mixing. Now there is a famous phenomenon for which arises due to these nonlinear processes, that is known as the intensity dependent refractive index. Self-focusing. So when a beam of sufficient intensity passes through an optical material, the index of the refraction of the material can be altered by the intensity of the beam. So this occurs in a manner like this: eta omega equal to eta naught omega plus n eta 2 omega I omega. In this expression, eta naught omega is the fundamental refractive index of the material. Fundamental refractive index of the material and then this term in eta 2 omega I omega is the nonlinear refractive index which is associated with the beam of intensity I omega. And now so these two contributes to the total refractive index eta omega of the material. Now this eta omega can be represented approximately with, so eta 2 omega is proportional to the chi, so it's a third order nonlinear effect. So this change in the index of reflection of a material with an optical field of intensity, so this is known as the optical Kerr effect. So it is present in almost all optical materials. Now the value of this n eta 2 sorry, sometimes I am calling this as n, so it doesn't matter because the refractive index in some book is written as n and some books it is written as eta. So eta 2 omega is typically of the order of 10 to the power minus 20 meters square by watt. This effect can lead to self-focus in a laser or amplifier rod, because a typical laser beam profile would have a variation of intensity within the rod. So basically it means that the laser profile is something like this. If we talk about the Gaussian mainly, okay, so this is the laser profile basically, but now here the intensity is very high, here the intensity is much lower, then here the intensity is far lower, and then here. Okay, so in this particular center here, so you can see that this is proportional to I omega. So here the refractive index will be higher, and then here the refractance will be lower. So basically this is a Gaussian beam when propagating from in a material. If the optical curve effect is there, then the refractive index will be here, the refractive index will be higher, and here the refractive index will be lower. So as you know, if the refractive index is higher, then the beam will start to focus towards that, right? So when we have this, then when the beam will exit this material, we will have sharp focused beam. So it is equivalent to using a lens here, so that will also create the, so that will also focus it to a point, and the output beam is something like this. Okay, so that's why it is called self-focusing. So here we are not using any lens or anything, it's just the beam that is focusing itself due to the nonlinearity of the material. So that's, so lens is particularly specifically used for the beam to focus at a point, but here the material is, the property of that material is affecting the beam to focus. That's why it is known as a self-focusing. So the amount of self-focusing that will can be determined by the B integral, which is given as 2 pi by lambda 0 L theta to I z dz, where the variation in the intensity with distance z in the amplifier material is taken into account. So the value of the B integral that leads to severe self-focusing and damage to the rod approximately C to 5. So this self-focusing focusing can lead to damage of the material. Now this method is also used as an advantage in the mode locking, which is known as curved lens mode locking. Now, due to this kind of phenomena, the study of this nonlinear optical material has gone from the last decade. So there has been an extensive effort in recent years to identify effective materials for such processes. In addition to having a large nonlinearity, these materials must be transparent not only at the laser frequency but also at the newly generated frequency. And other criteria that they need to fulfill. The first one is large nonlinearity. 2, transparent at the input and output frequency. They must be resistant to optical damage. Or have high mechanical hardness, high exhibit good thermal and chemical stability. Be capable of being grown in useful sizes. So these are the criteria for these nonlinear materials. First, it should have a large nonlinearity, which is obvious because we are talking about the nonlinear effects. Then it should be transparent at the input and the output frequency. That means that like you use a 1064 nanometer laser at the crystal and you want the second harmonic generation, so that means it will produce the 532 nanometer wavelength. So then you will have that. In order to have that 530 nanometer, the crystal should be transparent at both of the frequencies, that is at the 1064 nanometer and the 530 nanometer. The same is true for other nonlinear processes like in third harmonic generation. If you are using a 600 nanometer laser, then it will produce 200 nanometer. So the crystal should be transparent at 600 nanometer and 200 nanometer. Then they must be resistant to optical damage, which is obvious because uh, the effects like Carl lensing and other uh, thing like absorption, Carl lensing, this kind of phenomena can damage the optical material, so they must be resistant to optical damage, so their damage threshold must be very high, have high mechanical hardness. So these criteria are basically for commercial purpose. So have high mechanical hardness means that this material should be durable, not uh, like with a little bit of stress and strain this material will be uh, not unusable. So this material should have high mechanical hardness, and this material should exhibit good thermal and chemical stability. So by good thermal and chemical stability means that with this material should be non-interactive with the other chemicals, like available chemicals in there, like the material should not be interacting with the oxygen available in the air or something like that, so or the water vapor in the air. And have a good thermostability means that this material should have a large temperature range in which we can use the material, and be capable of being grown in useful sizes. So the size should be controllable. And then there is another condition, have appropriate phase matching parties. So we'll talk about this phase matching condition. Before that, need to recall that the second harmonic crystal must have no inversion symmetry, which suggests that only crystalline materials can be used, whereas third harmonic crystals can have inversion symmetry. Bulk second order nonlinear materials are generally inorganic crystals. A number of semiconductor compounds are useful for second harmonic generation when used in waveguides. Now I will write down some transparency region of some second order nonlinear optical materials. So these all are second order nonlinear optical materials. So LIB 305 has 0.16 to 2.6 micrometer. Beta BA B204, which is the BBO crystal, there is a transparency region of 0.19 to 2.5 micrometer. KNB03 is 0.40 to 5.5 micrometer. LINB03 is 0.40 to 5.0 micrometer. This is a 0.3725 micrometer. Then KDP is 0.2 to 1.4 micrometer. KTP has a transparency region of 0.35 to 4.4 micrometer. Then AGGAS2 0.5 to 13.2 micrometer. AGGAC is 0.78 to 118 micrometer. So these are the transparency region. So among this one is particularly famous for the second harmonic generation, which is widely known as BBO crystal. So whenever you use a BBO crystal, you will see this crystal is mounted in a rotation mount or a mount where you can have multiple degrees of freedom. So there, this is the rotation mount. You have that crystal, but in the proper mount where the BBO crystal should be mounted, it will have one is the rotation and two is the orientation of the crystal. So the crystal should not be like this, it can be like this, a little bit tilted and in angle. So let's say my palm of the hand is the crystal, so it's not necessary that the phase matching condition will be satisfied like this. So one direction will be this rotation, another will be this tilt, and another will be this tilt. So yeah, and so it's possible that this kind of orientation is perfect for the second harmonic generation, or this kind. It depends on which beam you are using to generate the second harmonic. Now the thing is that this BBO crystal, though we are talking about that this material should have good thermal and chemical stability. So this BBO has a good thermal stability, of course, but for the chemical stability, the BBO has chemical stability, but it can interact with the water vapor, and there can be oxidized layer created on top of the BBO crystal, which is not desirable for the second harmonic generation, and it can affect the BBO crystal. So BBO crystal are always locked inside their container whenever you are not using. Now we'll talk about the phase matching. So from the wave equation, Maxwell's wave equation, we can have this d2e3 by dz2 plus 2ik3 de3 by dz equal to minus mu naught square chi2 by 3 square by 2 pi square e1 e2 to the power I k1 plus k2 minus k3 z. So in this expression, e1, e2, e3 are wave amplitudes, and k1, k2, k3 are the amplitudes of the propagation vector of the three waves. So e1 E2, E3 are wave amplitude, and K1, K2, K3 are the amplitudes of propagation vectors. Now we can use the slowly varying approximation, so we can neglect the first term, that is this one, and use the second term only, and let us also define the delta k equal to k1 plus k2 minus k3. So dE3 by dz equal to I mu naught square chi2 omega 3 square by 4 pi square k3 e1 e2 where I delta k z. So this is a coupled wave equation. So this expression indicates how the amplitude of wave of frequency omega 1 and omega 2 coupled to produce a wave of frequency omega 3. So for the special case in which delta k equal to 0, the amplitude E3 will increase linearly with distance z. So this delta k equal to 0 is known as the ideal phase matching. So for delta k equal to 0, the amplitude E3 of will increase linearly with distance z into the material. So this condition is known as ideal phase matching condition. So it is the case described which the radiating dipoles of the material are phased with the field of the incident wave and thus continually add coherently to the beam as it propagates through the material. The total power emitted at omega 3 thus increases as the square of the number of atoms that participate in the interaction. So basically it is a dipole interaction. So here it is the case described as radiating dipoles of the material are phased with the field. So the intensity I3 emitted at frequency omega 3 can be obtained by solving this particular equation and then by integrating over a particular length, for example to 0 to L, and from there we can have a big expression of I3 which I will write C mu naught to the power 4 eta 3 chi2 square omega 3 to the power 4 e1 square e2 square 32 pi to the power 5 k3 square e to the power I delta k l minus 1 delta k square. So if we write this in terms of the product delta KL, we have I3 equal to C mu to the power 4 eta 3 chi 2 square omega 3 to the power 4 E1 square E2 square L square 32 pi to the power 5 K3 to the power 4 e to the power I delta KL minus 1 delta KL square. So the expression within the absolute value bars can be written as del. So this particular term which is I delta KL minus 1 delta KL square can be written as sine square delta KL by 2 delta KL by 2 whole square. So this is known as phase mismatch factor. Now converting the amplitude factors in 2 3 intensities and converting the frequencies to wavelength leads to the expression CQ mu naught to the power 4 chi 2 square I1 I2 L square 2 pi eta 1 eta 2 eta 3 lambda 3 lambda 3 square sine square delta KL by 2 delta KL by 2 whole square. So now this is a function of delta KL by 2. So when delta K equal to 0 for L equal to 0, the beam has not yet entered the material, making delta K equal to 0. So when delta K L by 2 is 0, that gives the highest value for this particular function. Now delta KL equal to 0, so for that L equal to 0 or delta K equal to 0, so this one is not feasible because that this means that the beam has not entered the material, and delta K equal to 0 is thus the process of phase matching. So that means that delta K equal to K1 plus K2 plus K3 equal to 0. For that again we can write in terms of refractive index K equal to omega by V, which is omega by C eta, which is eta omega by C. So eta 1 omega 1 C plus eta 2 omega 2 C plus eta 3 omega 3 C equal to 0. So for second harmonic generation, omega, so these two conditions needs to fulfill in omega 1 eta omega 1 eta 1 omega 1 by c plus eta 2 omega 2 by c minus eta 3 omega 3 by c equal to 0. And for second harmonic generation we have omega 1 equal to omega 2, therefore this equation becomes 2 eta 1 omega 1 equal to eta 3 omega 3. Now for second harmonic generation omega 3 equal to omega 2 omega 1. So here we have that the ideal phase matching condition for second harmonic generation is eta 1 equal to eta 3. Now the problem with that is this condition is not achievable because the frequency is dependent on the wavelength. So here the wavelength is being halved, so how can this refractive index can be equal? So that's why the second harmonic crystal are always birefringent. So the advantage of using this birefringent crystal is that in these crystals the velocity of two different polarization is different. So here this condition is matched for the two different polarization being like you know about the ordinary and extraordinary, so the phase matching will be extraordinary with ordinary or something like that. So that's why all the second harmonic crystals are birefringent. So otherwise this second harmonic generation with utmost accuracy is not possible. Now there are two principal methods for achieving phase matching condition in birefringent optical materials: angle tuning and temperature tuning of the crystals. For harmonic generation in shorter wavelength region where there are no optically transparent material, gases are used for harmonic generation. In that region, the phase matching is achieved by using two different gases with different index of diffraction. So in the shorter wavelength region, there are no optically so in this particular case gases are used. So in that region, phase matching is achieved by using two different gases. And then in order to describe angle tuning, we consider the case of uniaxial bireferent crystal. So as I was saying that if this is a PBO crystal or any crystal, then in order to have the phase matching, it is not necessary to have that crystal like this. It can be tilted like this or that, and then rotated. So in different orientation, this will be phase matched to generate the second harmonic precise. So in order to describe angular tuning now, we will consider a uniaxial bireferent crystal. So uniaxial crystal is that we will have the ordinary ray that is polarized perpendicular to the plane that includes the optic axis, and the extraordinary ray is one that is polarized in the plane of optic axis. This is the ordinary ray. Now this is the small angle between the K and C axis, basically theta, and then we will have the then we will have this 2 omega in extraordinary. So now the extraordinary ray is on, that is polarized in the plane of the optic axis and of opposing vector. So now here you can see that the phase matching is done between the ordinary ray and the extraordinary ray basically. And we also have the relation between the extraordinary and ordinary refractive index. So here this NE tilde is the principal value index. So this is the principal value of the extraordinary refractive index, and this is the uh, variable NE, and this is the NO. So NE theta equal to NE tilde for theta equal to 90 degree, and NE theta equal to N naught for theta equal to 0. So thus by rotating the crystal in the plane of optic axis and the incident beam, it is possible to select a range of values for eta E from which the condition of this condition, that is this one. So this condition can be satisfied. So for negative uniaxial crystal, where the for negative uniaxial crystal eta E less than eta naught, we would select the fundamental frequency as the ordinary ray and the harmonic frequency as the extraordinary ray. So the fundamental frequency as the ordinary ray. So this will correspond to the omega 1, and this will correspond to the omega 1, and for positive, so for positive uniaxial crystal, eta E is NE greater than N naught. So here it will correspond to the 2 omega 1, this will correspond to omega 1, and we will have the phase matching condition satisfied. Now we will go to the temperature tuning. So whenever the k vector and the optic axis are neither parallel nor perpendicular to each other, the ordinary and extraordinary waves tend to diverge from each other, since the direction of energy flow and the k vector are not parallel. So this limits the crystal length over which harmonic conversion can occur, and hence also the amount of harmonic power that can be generated according to the equation. So the extraordinary ray essentially diverges from the beam path, so the effect is referred to as walk off. And the second means of producing phase matching for condition in which walk off is present is that of temperature tuning. So in some crystal, the refractive index is dependent upon the crystal temperature. Thus, to achieve phase matching at specific wavelength, the temperature of the crystal is adjusted to a specific value and held constant to obtain the optimum harmonic conversion. So first is the angle tuning. We rotate the angle and then get the phase matching, and then there is a second, the temperature tuning, where the extraordinary ray will not diverge. Now here we have types of phase matching. So mainly there are two types of phase matching. Which can be accomplished in solid state optical materials. So type 1 and type 2 phase matching this are called. So in type 1 phase matching, omega 1 and omega 2 have same polarization. Of course, this should occur automatically for the process of second harmonic generation, in which omega 1 equal to omega 2 for a positive uniaxial crystal. The condition for type 1 phase matching would be eta naught 3 omega 3 equal to eta 1 e omega 1 eta 2 e omega 2 for a negative uniaxial crystal in eta naught eta e. Sorry. The condition will be eta 3 omega 3 equal to eta 1 o omega 1 and eta 2 o omega 2. So now the type 2 phase matching occurs when the polarization occurs when the polarization of omega 1 and omega 2 are orthogonal to each other, as might be the case for sum and difference frequency generation. Here the phase matching condition would be eta 3 0 omega 3 eta 1 o omega 1 plus eta 2 e omega 2 is for positive uniaxial crystals, and then eta 3 e omega 3 equal to eta 1 e omega 1 plus eta 2 o omega 2 for negative uniaxial crystals. So these are the conditions for phase matching type 1 and type 2. So whenever you go and try to buy a crystal and nonlinear crystal for third harmonic generation, you will see there is a heading that the critical phase matching is type 1 or type 2. So according to that, according to your need in the experiment, you will buy the crystal. Now the next thing is saturable absorber. Saturable absorption. So a nonlinear process that can be associated with real energy levels and population changes in those levels is that of saturable absorption. So this is a process in which a material can be highly absorbing at a specific wavelength when a low intensity beam is incident upon the material, yet an extremely intense beam will pass through the medium with little change in intensity. So this can be written in terms of alpha naught 1 plus I by I sat. So here alpha naught is the absorption alpha naught is the absorption coefficient. So this expression comes from the intensity dependent expression for the gain of a system, which we have already discussed earlier in the lecture videos, that is G equal to G naught by 1 plus I by I sat. This can be written as sigma UL delta N UL 0 by 1 plus I by I sat. So where this sigma UL is the stimulated emission cross section, delta N UL 0 is the population difference, and I sat is the intensity at which significant population change occurs. Owing to the presence of the beam, Now this delta NUL0 is defined as NU minus CU by GL and L, and NU and LL denote the population of upper and lower levels of the transition. So if the population in the lower level is significantly greater than the population of upper level, then we show that it was convenient to express the product sigma UL nu delta NUL in terms of an absorption coefficient, and then from here we get this particular expression. So saturable observer can be used to create a bistable element. This is the I1 in, this is the I2 in, this is I1 out, this is I2 out. So this is the output signal versus input signals from bistability. So a bistable element allows two levels of a beam of light to pass through the system and so provide switching from one level to the other by means of the optical beam itself. Such a bistable system is shown in this figure. So where the so for I1 in, the output is I1 out. Then as the input intensity of the beam is increased, eventually an intensity of I2 in is reached, at which the output intensity jumps significantly to the value of I2. From here it goes here, and then as the intensity is decreased, the output intensity remains high until a much lower value I1 of the input, I1 in the input is reached. So basically we starting from the I1 in and going to I2 in, and when we go to I2 in, the output is I2, but when we decrease the input intensity, the output intensity is not decreasing, rather than it is sticking to I2 out and it is decreasing to I1 out suddenly when we reach the input intensity as I1. So this is the bistability, optical bistability of this saturable absorber. So today we have discussed about multiple nonlinear processes, and it's a long discussion, to be very honest. So these nonlinear optical processes are only visible when we have a high intense pulse, but and as we know about the mode locking, so this mode locking can generate a femtosecond pulse, which gives you a peak power at terawatt or gigawatt. Okay, so this high intense so this intense pulse when used in material, so this material gives us the nonlinear effects, and that depends on the anisotropy of the material. So there are multiple nonlinear effects. Apart from the linear part, we have this second order polarization, the third order polarization. In second order nonlinear effect, we have the second harmonic generation, where we use a input beam has angular frequency omega, and the output beam has the angular frequency 2 omega, and then we have the sum and difference frequency generation, where the input beam has a frequency omega 1 and omega 2, and we have 2 omega 1, 2 omega 2, and omega 1 plus omega 2, and omega 1 minus omega 2 as the output beam. Now then we have the optical parametric oscillation, when we have a beam of frequency omega 1, and then we generate a signal of frequency omega 2 and idler of omega 3. Then we have the third order nonlinear optical process, where we use one frequency and we get omega 1 frequency, and we get 3 omega 1, and from there we have the Fourier mixing, where we use three different frequency omega 1, omega 2, and omega 3, and we get omega 4 as the Fourier mixing signal. And then we have the intensity dependent refractive index. So these are the main nonlinear effects. So in nonlinear intensity dependent refractive index is used in the self-focusing or the curl lensing, which is a very useful method in case of mode locking. Apart from that, there are also other nonlinear effects, but what mostly important is that as we have learned about lot of laser things, so we need to know where this laser is actually can be used. So these are some applications in the nonlinear optics of laser, especially the pulse laser. So today I am going to stop here, and this is the last problem solving session. So thanks for joining in this course and attending all the problem solving session. Thank you, and I will end today's session here.